So let's continue with the Hamiltonian formulation. Last time we wrote down the Hamilton's equations, which are the equations of motion in this formulation. Let me write it down again. So our equations of motion. So if you have coordinate q, k, and you are looking at the time derivative of this, you have to take the Hamiltonian and differentiate it with respect to the momentum pk, which is conjugate to qk. Okay, and then you have pk dot as delta h over delta q k, and there should be a minus sign. Let me check which one has minus. Pk dot should have a minus sign. Okay, so these are your Hamilton's equations. They are also called Hamilton's canonical equations. And sometimes just canonical equations. Okay, so they go by all these three names. And you remember that our Q and P are at equal footing now. And that is why we were working in the phase space. Okay, so this is given. Let's say I take some function f, which is a function of these coordinates q and conjugate momenta p and possibly time. Let's say some function f is given, which is a function of q, p, and t. Okay, and we ask how this function will evolve with time. Okay, and its time evolution will be governed by the time evolution of q and p, and of course the explicit time dependence, and these are in turn determined by the canonical equations. So let's find this out. So we are looking at df over dt, which is f dot, and this is, so df over dt is delta f over delta q, or del f over del q, q dot. Okay, and let's put this. There is a summation over k implied. Then you have del f over del p, p dot. Okay, summation over all the conjugate momenta, and because of the explicit dependence on time which I have shown here, you will have the partial time derivative. Okay. Now in this I can substitute what you have here in the equations of motion. So qk dot will become del h over del pk, and pk dot will become minus del h over del qk. Let me write that down. So you have delta f del f over del qk. Qk dot is del h over del pk minus, because of this one, del f over del pk, and pk dot is del h over del qk, and then you have the partial derivative with respect to time. Let me make the summation explicit here for once. Okay, now I define what is called a Poisson bracket. So I will define Poisson bracket between f and h. Okay, this is denoted by these two curly brackets. So the definition is, you whatever you have in this this first term, not the first term, but these two terms together form the Poisson bracket. So the definition is, I think instead of writing it again, let me just show it here. So this is defined to be the Poisson bracket of F and the Hamiltonian H. Okay, so with this I get F dot to be equal to the Poisson bracket of F and H plus the partial derivative of F with respect to time. Okay, and slowly it will emerge that this Poisson bracket is a quantity of fundamental importance, but for now at this juncture it is just a definition and a simple way of writing, but we'll see eventually it is quite an important quantity. Okay, that's good. And note that this definition, this thing is antisymmetric in F and H. So if you interchange F and H, this will be antisymmetric. Okay, so that is why I'm going to write it in a slightly different, not different, but the same thing I will rearrange and put it this way. So I'll write del F over del QK, del H over del PK minus del H over del QK del F over del PK. Okay, and there's a summation over K implied. So all I've done is in the order of derivatives is kept the same, del over del Q, del over del P, and in here also you have del over del Q and del over del P, and only the order of F and H is interchanged in these two terms. Okay, so it's clear it is antisymmetric if you interchange F and H here. Okay, that's good. Now if your F is a conserved quantity, meaning if it is an integral of motion, then your F dot is 0. So if F is an integral of motion, that is df over dt is 0, then you get F Poisson bracket H to be delta F partial derivative of F with respect to time. And if further this quantity does not depend explicitly on time, then you get the condition to be this for conservation of F. Okay, so let me write this down again. If you have F, which is a conserved quantity, and it depends only on the Q and P and not time explicitly, then if you take the Poisson bracket of F with H, you get 0. Okay, so this implies that F is conserved. Okay, now that's good. Now let's take in turn F to be Q and then P. So I take once F to be equal to one of the coordinates, and then I will take F to be one of the momentum, conjugate momentum. Okay, so F is one of Q, K's, and this, and substitute in the definition of the Poisson bracket. So let me put it here, and you can check that you are going to get the following. So if you look at Q dot of K, then you are going to get Q, K, H, this Poisson bracket. And if you look at P dot of K, then you get P, K, H. Okay, so your equations of motion which are here, the Q dot and P dot which you write in terms of the derivatives of H, now become the following. Okay, let me put a border around this. Now see these equations of motion appear very symmetrically for Q and H. The annoying minus sign which was there is not here now, but that's a minor thing. But you see, it looks, the two equations here, they look identical. The only thing is Q is replaced by P in this one. So this also emphasizes the fact that Q and P are being treated equally in the Hamiltonian formulation. Okay. Now what I'll do is I will take this definition of Poisson bracket of any function f with h and put it and use it to define a more general quantity, not more general but just Poisson bracket of any two quantities f and h. So here is the definition: Poisson bracket of f and g. Okay, so you are given two functions f and g, where f is a function of q, p and t, all the coordinates and their conjugate momenta and possibly time, and the same for g. And then I define f and g, the Poisson bracket of these, to be del over del qk del over del pk minus del over del qk del over del pk, and then I put here f and g here and g and f here. So that's the definition of this Poisson bracket. Okay, we can immediately see certain properties which I will list down. So one property is, of course, antisymmetry. Which you can see immediately from the definition. So if you interchange g and f, their positions within the bracket, you pick up a minus sign. Okay, so next, if you take the Poisson bracket and take the Poisson bracket of one function f with a constant, you are going to get 0 because the derivatives of the constant will give you 0. So let me put it down. C is a number here. Also, the Poisson bracket is linear. So if you have C1 F1 plus C2 F2 and you take a bracket with G, it will give you C1 F1 G and C2 F2 G. Okay, so this is your linearity. Then the product rule is the following. So if you take the product of two functions f1 and f2 and find out the Poisson bracket with another function g, it will turn out to be f1 f2 g plus f2 f1 g. So that's the product rule, which you can easily verify starting from the definition of this Poisson bracket. Then if you take a partial derivative of the entire bracket, then you will see that the partial derivative with respect to time, that partial derivative distributes. So you take del over del t of this Poisson bracket and you can verify that the following holds true. Let me write down partial time derivative distributes. Okay, one more thing you can verify. We have listed down 5. Sixth one, you can check that that Jacobi's identity is also satisfied. Because it's an identity, it holds true for any f1, f2 and f3. So let's say you are given three functions, f1, f2 and f3. So you construct a Poisson bracket, and finally we have the Jacobi's identity. So let's say you have three functions which are this is the sixth property, right? And this is 5. Somehow it has become brown. Okay, anyway. So if you are given three functions, f1, f2 and f3, then you can take the first f1 and f2 and make a Poisson bracket, and then you can take the Poisson bracket and create a new Poisson bracket with the third function. Now you cyclically permute the three, so I shift f3 to here, f2 to there, and f1 to the first position. Okay, so it will become f2, f3 with f1 plus, let's do it again. So f3 comes here, then f3, f1 and f2 becomes the last one. So if you add these three up, these will be identically 0. Okay, and the reason it is called an identity is because it doesn't depend on what f1, f2 and f3 are. And that holds true for any three functions of q, p and t. Okay, so this also you should verify by using the Hamilton's by using the definition of the Poisson bracket. Okay, so these are the properties that I wanted to tell. Now also let me try to see how to change this color. Yeah. Okay, so now if let's say I take the Poisson bracket of a function f with either q or p, okay, and you will see that it will generate the partial derivatives with respect to momentum or the coordinates. So please verify the following, that if you take a function f and you take a coordinate qk and construct the Poisson bracket, you are going to get the partial derivative of that function with the conjugate momentum q pk. Okay, and in this case there will be minus sign, and if you take f and pk, then you are going to get del f over del qk. Okay, something nice has happened, and it is no more it is no more pixelated, which is very nice. For last few videos I was getting a pixelated writing, so that's nice. That is plus. Okay, so that's nice. You can generate the partial derivatives of these functions by constructing the Poisson brackets. Now I'm going to tell you a nice theorem, and this is called Poisson's theorem. Let me go to the next page. Let me write down Poisson's theorem. Okay, so suppose you are given two integrals of motion, f and g. So you are given f, which is a function of coordinates, all the momenta and possibly time. Okay, and another function g, again depends on q, p and t, where q and p run from 1 to n. I mean q1, q2, so on and so forth. Okay, and we say that let's say these two are integrals of motion, meaning the total time derivatives of both of these is equal to 0. So let f and g be the integrals of motion. That is, they are conserved. Okay, if that is so, then f dot is 0. And remember, when I put a dot, it's a total derivative. Okay, f dot is 0. And your g dot is also 0. Now, let's construct Poisson bracket of f and g and ask what is the total time derivative of this new quantity. Okay, that's what we want to do. So if you remember, let's go back here somewhere in the beginning. Yeah. So if you take a total time derivative of function, it's equal to the partial time derivative plus the Poisson bracket of that f with the Hamiltonian, okay, of that system. So that's what I'm going to do. So you are going to have fg. This is what you have right now. So you have to take a Poisson bracket with the Hamiltonian of the system plus the partial derivative of f and g, this Poisson bracket with time. Right? That's what you had in on that slide. So let's evaluate this. This one is easy. We will use this property that it distributes. Okay, so you please show that this is true. So I'm going to distribute the time derivative, partial time derivative over these two. Okay, so here let me write delta f over delta t with g and f delta g over del g over del t. Okay, that's good. Now this one, it's three functions, so I can use Jacobi's identity, which will just cyclically permute. But the advantage is that it is going to generate those two terms which you have in Jacobi's identity, but h will be in that case sitting with f in one term and it will be sitting with g in the other term. Okay, so you'll be having Poisson brackets with involving f and h and g and h. That's why I'm doing this. So you put here, so let's permute. So of course you are going to get minus signs with these terms. So yeah, so let me take f here. So it gives you g h f. That's one term. The second term will be generated by shifting further. One more shift, so it will be h f and this entire thing with g. Okay, so this is what you get. Now also remember, go back here, this is what I'm trying to do. So I'm going to combine so that I get df over dt. Okay, so this is what the task is in front of me. Where is it? Yeah. So let's take this term and this term first. Okay, so this has f as the first term. So I will, if I do interchange these two positions, this will, because of antisymmetry, this minus n will be gone, and then I can use the linearity to combine these two terms. Okay, so it will become f Poisson bracket delta g over delta t plus gh. Okay, and the same thing for the other term. Something is off. GH, yeah, nothing is, everything is fine. So here you have h first, so when I interchange these two, it picks up a minus sign, and but then minus sign will come out, so you'll get you'll get f and h. So first will be f and the second h, and you can combine with this one. So you get del f over del t plus Poisson bracket of f and h, and this entire thing you combine with g to make a Poisson bracket. But now this is f comma, this is what, dg over dt, g dot. Okay, that's what you have seen already. Let's go back again. That's your g dot, partial time derivative and Poisson bracket. And this one will be del, no, not del, f dot with g. Okay, and because g dot and f dot are 0, because we have assumed them to be conserved quantities, this is going to be 0. And that's the proof of Poisson's theorem. Okay, so you see that if you start with two integrals of motion f and g, you can in principle construct another integral of motion, which will be f, Poisson bracket of f with g, but that will not necessarily be a new integral of motion. Okay, because there are only a fixed number of integrals of motion for a given system. So if your system is n-dimensional, okay, let's say n generalized coordinates describe the system, then you know that you will have a total of 2n minus 1 integrals of motion. Okay, so you can imagine that the total number of constants which you will get by doing the integrals, okay, will be 2n minus 1. You can count it this way. So you know that to describe the evolution of your system uniquely with time, for each coordinate you need to tell where it is at a specific time, initial time, and also the velocity at that time. So if there are n coordinates, you get total 2n. Okay, and one of these can be chosen as time, and you can choose, you can remove that time for, you can shift the origin of time, so that will be gone, and this you can do for any closed system. If this is what you're hearing for the first time, I don't recall whether I have told this previously in the course. If not, then you can, this simple example will help you understand. So imagine you are looking at a harmonic oscillator, one-dimensional harmonic oscillator. Okay, I've put the constants to be all the masses and the spring constants to be unity. So this is one-dimensional, and for this you know the solution. That solution is x is a cos omega t plus phi. Okay, so you have two constants, a and phi, which is what you expect. But then you can remove the phi by shifting the origin of time, right? It can be just removed. So instead of 2, you get 1. But if you imagine you had several harmonic oscillators, they all will have some different phases, but you cannot remove all the phases. You can shift the time and remove one of the phases. All the other phases will just get shifted, but they will be there. So you see, if you have n oscillators, you will have 2n minus 1 constants. And the same thing is true in general. You can convince yourself. So if there are 2n minus 1 such constants, such integrals of motion, so clearly you are not going to generate new constants of motion by just taking Poisson brackets. Okay, you may or you may not, depends on what you start with. Okay, so it is not necessarily true that if your f is a constant of motion, your g is a constant of motion, then you will get a new independent constant of motion. This may again be a function of f and g. This also, for example, may be just a function of f and g, so you don't get anything new, but you may also get new constants of motion. So this is a useful theorem. And before I stop this video, I want to give one small exercise and derive this nice result. So show that if you take coordinates qi and qk and construct the Poisson bracket, you get delta ik. Similarly, if you construct pi with pk, you get again delta ik. So unless the two coordinates in this Poisson bracket are the same, you get a 0. If they are same, you get 1. Okay, the same is true for momenta, which is nice. I mean, look, it again looks completely identical with respect to q and p. There is no distinction between these two. And also you will see that if you take qj with pk, you get delta jk. Okay, so I'll stop here and we'll continue in the next video. Please do all these exercises and also show that these results are true. These are trivial to show. So please do so, and let's meet in the next video.